Welcome to this very special session of Shadow the Scientist. My name is Jamika Marshall, and I am your session host and the Shadow the Scientist Programs Manager. Now, Shadow the Scientist is an initiative that's offered by an amazing team at the University of California at Santa Cruz. This special session is dedicated to you, the 2025 cohort of the Akamai Workforce Initiative. And so I see all of you there in a separate screen. Hello, I think I said I greeted each of you. I see you waving. Thank you so much. I'm so excited to have you here shadowing the amazing Gemini science team. Now, the Akamai Workforce Initiative is led by the Institute for Scientists and Engineer Educators at the University of California, at the University of California Observatories, and right here with the University of Hawaii at Hilo. And I am pleased to say that this has been going since 2001, so 24 years. You are part of an amazing legacy, and I'm grateful to be able to be a part of your experience here this summer. Now, this evening, we have a very, very special team here to host you. And before I get started, though, let me give you just a bit of background on the International Gemini Observatory. Now, the International Gemini Observatory consists of twin 8.1 meter optical infrared telescopes located on two of the world's best observing sites. You are here with us in Hawaii, so the Gemini North telescope is located near the summit of Maunakea and is a part of an international community of observatories. By incorporating technologies such as laser guide star adaptive optics and multi-object spectroscopy, astronomers in the Gemini partnership explore the universe in unprecedented depth and detail. Now, tonight's observations will take place right behind me in the Hilo Base Facility control room, with the shadowing happening just down the hallway from me in the conference room. Now, we have some amazing science hosts and science team members here with us this evening. Jenny and Adam are going to be who we're shadowing throughout the evening. Now, our science hosts who are going to be our guide through this whole experience are Brian Lameau and Cicero Liu. I'm going to stop my share so that we can jump right in with Cicero and Brian. Cicero, Brian, welcome.
Aloha, aloha guys. Sorry, I didn't really talk to you before. Hi everybody. I'm Brian. I'll introduce myself more fully later, but yeah, I'm here. I'm here for the next couple hours hanging out. A lot of times I'm over in that room doing the driving, or well, actually mostly doing the instruments. Yeah, I'm a staff scientist here at Gemini North. Cicero.
Cicero. I started about a little less than 2 years ago here as a science fellow, which took part 50% of my time helping the operation of Gemini, and 50% of the time doing my research. I'm essentially a postdoctoral researcher here, and this is an incredibly welcoming environment, and it's really nice to be able to work with Brian, Jamika, Adam, Jenny, and many more team members.
Yeah, so we have, I think, something like 80 staff here. Normally, we have 2 in the observing room tonight, so a lot of pressure on those 2 to get it right. But we have 78 people during the day, including you. Well, so who here is doing their internship at Gemini North? Okay,
Brian, just to let you know, we're starting to the boss target now.
boss target. Okay, thanks.
I'm gonna start with the mascot of the beam because it might be so free.
Okay. Yeah. So y'all are helping us too. It's an awesome team. And I guess some of you have been to the summit already. Yeah, to the summit facility. You went up there. Okay, so you got to see the actual telescope, and some of you were working on engineering projects. Is that right? Here. software engineering or hardware engineering? Okay, yeah. So there's a whole division of people that do like hardware engineering, people that do software engineering here, people that do outreach and community engagement, people that do science operations. Cicero and I do research in our spare time, let's say. And so we actually use the telescope for this telescope and other telescopes for our research. So yeah, cool. So they're actually observing right now. And so we're going to shadow what they're doing. They're actually setting up on a target. So before we do introductions, I'm just going to jump right into it. So let me share my screen.
Yes, and while you're sharing your screen, Brian, let me reintroduce our amazing team in the control room. This is the Hilo Base Facility control room. Yes, a Hilo Base Facility control room, and it's Adam Smith and Jenny Bergheis. I wanted to make sure I got that right. Jenny Bergheis and Adam Smith. All right, so now Brian's sharing his screen. Let's see what's happening on the summit. Brian, are those clouds?
So yes, they are, unfortunately. Ick. So is everybody here doing an internship with the Maunakea observatories? Yeah, everybody? No? No? Yes? Okay, so most people in the room are doing something with the Maunakea observatories. For those that are not, I assume you've seen Maunakea before?
Yeah, once or twice.
Once or twice. Okay, yeah. So this is a picture of Maunakea from near the summit. So where the Gemini North telescope is on the eastern ridge. And we have light sensitive cameras that are pointed in different directions. And this is actually the same setup that they have duplicated in the observing room there. So we don't have anybody at our summit facility observing at nighttime. So the telescope there's nobody there. And so Jenny and Adam are running the science operations. Jenny is in a role called operator tonight. So she is in charge of the telescope's health and safety. She needs to monitor the conditions on the ground, the conditions inside the telescope dome. We have to have near 1,000 sensors up there because we don't have anybody actually physically looking at the telescope. And if we did, we would need still 500 sensors or so. So there's just a little bit of information here on this screen that helps both Adam and Jenny understand what the conditions are in the dome, on the telescope, and in the sky. And so Adam is in a role called observer tonight. So he is in charge of the scientific program for the evening. So we work on Q observing. What other telescopes y'all work for? Subaru? Okay. So Subaru does some Q observing. So like the prime focus spectrograph is Q observing. Hypers prime cam can be Q observing, but they also have classical nights. So people come and they actually observe their program and they get whatever conditions they get for that night. And if the conditions are bad, then oops. Yes. If the conditions are bad, oops, you lose that night, and then you have to wait another 6 months or a year in order to observe. So I've been on the short end of that many times. My research group, I come from California originally, and so we would fly all the way out here, and then we'd get all excited. We'd have our half night on Keck or Subaru, and then freezing rain, and that's it. And then you got to convince people again that your idea is good, and then earn time on the telescope. So that's the classical part of observing. We're on Q. So Q means that, so Gemini is one of the only telescopes where everybody in the world can apply. We have an open skies policy. So you have a good idea, you send in you say, hey, this is my idea. I want to observe this particular object, or I want to observe this class of objects. And there's a international panel of scientists. They say, yes, that's a great idea, or no, that idea sucks. And for the great ideas, it's only about 10% of people that get time on the telescope. So 1 out of every 10 proposals gets time. And so then we throw this into the giant pool of observations. And you actually have to say ahead of time like I can deal with some clouds, or I can deal with some turbulence, or no, I have to have the best possible conditions. And so Adam's job tonight is to assess the conditions in the sky, on the ground, and say, okay, from this pool of potential scientific observations, this one seems well matched to it. And so we'll go ahead and take that observation. So you can see here, there's a bunch of clouds. That's not good. Turns out clouds, block light. That's not good for astronomy. We are an optical near-infrared telescope, so it's not as bad in the near-infrared. But actually, we are observing in the optical. And this is the target that we're observing right now. So this is what Adam is setting up on. And so he's using an instrument called GMOS, which is the Gemini Multi-Object Spectrograph. We have very clever names. And so let's see.
Can I say how beautiful that spiral galaxy is? That is just gorgeous.
Yeah, so I just want to point out, this is not our image. We can't take credit for this. This is the Digital Sky Survey image. So this is a piece of software that we use so that all of the scientists who propose for observations on our telescope, all of the staff here that vet those observations, so that make sure that the observations are good during the daytime, and the nighttime observers and operators, they all use this tool. And so this tool tells us, basically, we have a pre-image of the thing that we are going to observe. So this is taken with a smaller telescope. It's taken a while ago. And we use the parameters of that image. So we look for stars, for example. So you can see this red thing right here. This is our guiding star. So we want to make sure that we stay in the same location the entire time that we're observing. We want to get every single photon that we possibly can. Our job is to be as efficient as possible in our observations. And so this guide star will keep us within 0.1 arc seconds or better for the entire observation. That's actually, we want precision a little bit better than that, but that's the basic goal. Do you guys know how much an arc second is? Yeah, everybody's comfortable with arc seconds?
1,600 degrees.
Exactly, yeah. So like night sky, so if you went outside, what's a familiar object that would be like roughly a degree? Or how do you determine what's a degree on the sky? Anybody know? Yep, pinky finger, index finger, whatever. So arm's length, index finger, close one eye. That basically covers the full moon.
Parts of.
So that's 1 degree. So 1/3600th of that, that's 1 arc second. We do better than 0.1 arc seconds for the entire observation. So that's 1/36,000th of a fingernail. Yeah,
Okay, just for y'all, I'm doubling the exposure time on this mask out of beam image.
So they're actively taking images right now, trying to determine how to set up this target. So Adam's taking an exposure right now. He's going to take an image of this field. Let's see if we have the.
Oh, is this one done to?
Adam, is that SegPod active?
Yes.
Okay.
Should be.
So this is a multi-object spectrograph target. How many people are familiar with spectroscopy? Is any, for people that are not familiar, heard the term before? There's basically 2 things that we do in astronomy. We take pictures or we make rainbows. Those are the 2 things. So, oh, nice. Okay, so this is actually our image right now. Okay, this is an image. So this is first things first, take a picture. So this is a picture, looks a lot like the archival picture over here, but more beautiful, obviously, because we took it. So this is an actual picture of the galaxy on the sky right now. And so we are going to disperse the light. So that's what spectroscopy is. you put a dispersing element in front of the light. So that could be a prism, or that could be a diffraction grating. Those work on two different principles, one on refraction, one on diffraction. And you disperse the light out into a rainbow. And so the idea is to measure the constituent parts of the light. So when you take an image like this, it's basically just a big light bucket. You're just taking all the light from a certain color, let's say, and you're just all throwing it into this picture here. When you put a dispersing element in front, you actually break it up into its constituent parts so you can measure more precisely the physical properties of that source. So this just tells you, if you take like an image in green, let's say an image in red, you can determine the difference in like, oh, that galaxy is more green than red, and that can tell you something about the galaxy. But it can't give you super precise information on the galaxy. So if you want super precise information, you have to take spectroscopy. And so multi-object spectroscopy is when you put a bunch of, say we have a carbon fiber mask, and actually our laser room is right down the hall. So we have basically a chunk of carbon fiber. We take a lasing machine, which is broken right now, unfortunately. But in theory, we would take this mask and we'd stick it in the machine, and we'd have a pre-designed, basically a file that we would ingest into this machine. And that file is a mask design file. So the person proposing for this observation would say, oh, I'm interested in this part of that galaxy, this part of this galaxy, this part of this galaxy, this part of this galaxy, different regions. This particular one is looking, I think, at globular clusters. So old, tightly packed groupings of stars that are thought to have existed basically since the beginning of the universe. And so they're gonna, they would take an image like this, or they would have an archival image from a different telescope, and they would determine, yes, these are the locations of the galaxy that I'm really, really interested in. And you take a slit, and so you block out all light except for that exact portion of the galaxy that you're interested in. And so when we go and laser mill things, we have a precise definition and say, okay, only this portion of the galaxy we're interested in. So that when we put it in our optical path, so telescope collects the light, it funnels it down into this instrument, and we see this picture here, we know exactly the properties of the telescope, of the instrument, of the portion of the sky that they're looking in, and we block out everything except for what those scientists are interested in. After that, we disperse the light. So we put in a grating, so a diffraction grating, and we, for every single portion of the galaxy that they're interested in, we have a spectrum. And that spectrum, in this case, is going to be optical. So it would be like a rainbow. So it would go all the way from about 400 nanometers, which is roughly where we see blue, to about 800 nanometers, which is roughly where we see red. So we observe in the optical. We also observe in the near infrared. We can do the same exact thing in the near infrared. That image back there, that's probably a false color near infrared image. And so just like in the optical, there's blue and red in the near infrared. You
Can I give you
create
some
a
offsets?
rainbow out of that as well.
Yep.
So this was an image that Adam took with the mask out of the beam, this carbon fiber mask out of the beam. Once he's comfortable with this being in the right place, so he's gonna ask Jenny to move the telescope around just a little tiny bit, and then he's gonna put the mask in the beam, and we have little alignment boxes basically. So there's stars.
Negative 0.37. Q positive 0.17.
So he's making movements that are sub-arc second right now.
Q
So he's asking Jenny, so
positive
he measures
0.17.
slight offsets of these stars. And he asked Jenny, can you just move just nudge the telescope about 0.1 arc seconds in the up and left and right directions. So he just asked for we have this coordinate system P and Q. It's basically wherever we are, it's up, down, and left, right. It's in the reference frame of the instrument. And so he asked for a 0.1 movement in the up, down direction, 0.1 arc second movement in the left, right. Now he's gonna take another picture, probably, and he'll measure, okay, are we in the exact location that we want to be? Then he puts the mask in, And then we have these little boxes that are supposed to be aligned with stars that are around the galaxy. And he'll take another image. He'll see if those stars are aligned. If yes, cool. That means that all the stuff that we can't see in an individual image is aligned as well. That's how we design things. And then we put in the dispersing element, and then we take a spectrum. All clear? You guys ready to go in and operate the telescope?
Yeah.
Yeah, good. Okay. We'll put you on Subaru first. Okay. Train on Subaru. Less scientific leverage there.
I know how to operate them.
Okay, so we'll come back to this in a second. So I'm just gonna share some slides quickly. Okay, so there's no serious plan for tonight. We're gonna follow wherever the universe takes us. We'll do like just some basic stuff about Gemini and about the instruments that we have, about how telescopes work. And if you guys have any questions at any time, just interrupt us and ask questions. And we'll probably go back to the observing room as soon as they're like on target. Yeah, so yeah, Wednesday.
Concepts with rotation.
So do you have to cut a new mask for every different observation?
We do, yeah.
A lot
So
of cutting.
yeah, so this particular program that we're about to observe, their request is for 6.5 hours of integration per mask. So because of the way our cameras work, you can only take observations at 20 minutes at a time. So this is building up 18 to 20 observations over the course of 6.5 hours, but usually it's over many different nights. So we use that mask for that observation, and then that mask becomes a souvenir for the science team if they want it, or it gets recycled and then we make new masks out of it. So any
Well, actually, we
program.
could store it in a drawer here, and I was gonna say, Sister O'Brien, if you want, to grab one from one of the drawers here to show them, you're more than welcome
Okay.
to come in.
Okay.
I can
Awesome,
just give you a
yeah.
baggie of them.
Awesome. Okay, I'll go grab it.
Thanks.
Thank you, Anna.
And this could even be over the course of years. So actually, we just observed a program that the science team has been trying to observe for 3 years. So 3 years we had masks that were left over from 2022, 2023. They'd even shipped some down to Gemini South, and then they came back. And so it's very hard to get a long integration with a world-class telescope. So this team was looking at like 15 different clusters of galaxies in the distant universe. And they had 3 masks. So they had something like 45 masks total. So they probably were the ones who broke our lasing machine. Yeah, and it took a long time. So I have programs that I've observed on Keck, which I kept the same mask for 6 years because we just didn't get enough integration time. But yeah, every single program needs one. And at the observatory, we have one mask making machine. It's sitting there. We have a twin, near twin in the south. So when they need masks, Adam and Jenny go and laze them. And then we actually ship them down to Chile, or if a staff member is going down to Chile, we put them in their suitcase and then we bring them with us. So yeah.
Wait, so Brian, Gemini South does not have its own machine for making the mask?
They do. It's been broken for quite some time.
Oh,
So
I see,
yeah,
I see.
unfortunately, it was a kind of catastrophic failure, and it was going to require a lot to fix it. And so we came up with this method of having
Of us doing it all
most of the
for
math
them.
done here.
Got it.
What's that, Jenny?
Working for a while, and theirs was working for a while, and for a year they cut our masks. And now it's been, I think, 5 years of us cutting their masks.
Yeah, ever since I've been here.
Yeah,
Nice.
over that.
Is there any F2 masks in there?
Tiny masks.
Those are the small ones. Those all look like GMOS masks.
Okay. No. Is it a different shape?
It's a different shape, yeah.
Okay, starting science. All good. You want to take another sky?
I don't know. how it looks like.
No, they're like this big.
Yeah, if you want to.
Okay, just a minute.
Yeah, I'm like, work. What are they made of? Carbon fiber. Carbon fiber, yeah.
This is
Yeah, so when you guys look at them, you'll see like horizontal or diagonal strips. Those are the slits themselves, and then little boxes. That's where the stars go. So maybe Adam has a picture of this. Yeah, so this is like an image that he took of the mass that's currently in, and you can see the boxes here. 1, 2, 3, 4, and then you can see some of the slits here as well. Okay, so this is me.
we're
We're gonna
good.
do introductions. So this is me. I'm Brian. Hi. Met you guys before. I work at Gemini North. That's where we are. This is taken from probably Carl Smith. So yeah, Maunakea, you guys know it. You can see Gemini North from Hilo along Canada-France Hawaii telescope, the UH 88-inch telescope, and sometimes on a good day, the Euclid telescope. I've been an astronomer for half my life. I come from California. I've been coming to Maunakea for 22 years now. So I actually first observed on Keck when I was an undergrad. Yeah, that was a terrifying experience. My advisor fell asleep and I had to take over the telescope, not knowing what I was doing. I do research on very distant galaxies and clusters of galaxies, so big conglomerations of galaxies. You guys know Andromeda? Close by galaxy? Yeah, so it's a little bit bigger than the Milky Way, gonna crash into us in 3 billion years. It's no big deal. So clusters of galaxies are like same distance Milky Way Andromeda. If you take like a circle or a sphere, same volume, but instead of containing just 2 major galaxies, they contain anywhere between 100 and 1,000 galaxies. So these are the densest portions of the universe. I look for these structures when the universe is about half its age, all the way to about when it was 10% of its current age. So this is just an animation based off of real data that we took with Keck and the VLT telescopes down in Chile of a supermassive structure in the early universe. This is the mass of this thing is about 5 billion million times that of the sun. So pretty massive. And each one of these is like a Milky Way type galaxy. Yep. And my wife's an astronomer. She works for UC Santa Cruz. You guys should probably know that one. And actually, I worked with the Akamai program in 2003 when I was an undergrad at UC Santa Cruz, when it was called the Mainland Exchange Program. So I had a colleague there from Hilo that came over to UC Santa Cruz to do some adaptive optics work with me. And this is Eris. This is my son. He was born in Hilo 2.5 years ago. All right, Cicero.
Ooh.
That's you, I think.
Oh, that's me, I think. Okay, well, I've been here since fall of 2023, just the start of September. So I'm very excited for the first time to see Gemini on the summit, which you can see is the upper left picture. I also am trained as an infrared astronomer, so I use a lot of infrared telescope as well. So there you see me on the left side, lower left. So that's IRTF. That's the NASA Infrared Telescope Facility. So it's a much smaller telescope mirror. So its diameter is about 3.5 meters, which is less than a half of Gemini. But it's very effective in producing high resolution spectroscopy, so making very, very fine rainbows. So you can measure what's exactly in those rainbows and the information. So IRTF operates classically, as Brian has mentioned to you. So essentially what you do is I am my co-PI, co-investigators, travel to Halipahu the night before to get acclimated. So we get some headache, stayed up for some more, and then chatted, and then spend the morning sleeping. And then the second night, we go all the way to the summit and spend a whole night there. So that's how it worked. They have, instead of Gemini, it's a lot more structure, and we have 5 floors. IRTF only have 1 floor, and it also got different kind of instrument than us. Okay, so that's
And Gemini's in the minority because there's still a lot of observing that happens on the summit. Tech still sends at least 1 person to the summit. Subaru usually 2 people, although sometimes the science team can go up if they're really, really nice. IRTF, who else? HT sometimes, yeah.
SMA probably still observes it.
Some of it, but most of it. Things.
Yeah, some millimeter arrays have the nicest observing room, which is oxygenated, and you don't feel like your head's popping.
So you go outside.
So, yep. Okay, so I do something that's completely near and dear to us. So looking at how planets are formed. So very different flavor of research than what Brian does, and which is on the other side of the universe. So on the right-hand side, top right, you can see that is a young planetary system, just like ours, except the star is about 1.8 times more massive. What does that mean? That means it gives a lot of radiation to the structure of the planetary system that we can see it more directly in a direct light. So you can see that the center is actually scooped out. That's because the center of the star is too bright. So they put a coronagraphy, which blocks the light from the central star. And when this light reflects off from the dust and the planets in that system. So you can see that there are 2 very nice rings. So they resemble the ones, the asteroidal belts that's in between Jupiter and Mars, as well as the Kuiper belt that's exterior to Pluto, or the minor planet. So I study how planets in these young planetary systems really form. Turns out, actually, I'm gonna let you guys guess. So there's 3 pictures on the bottom of the slide. So one is the green sand beach, one is the volcanic rock, and the other one is quartz. So who would have guessed most of the exoplanetary system, exoplanets actually form from green sands? Show a hand. Nobody thinks so? Okay, what about volcanic rocks? Do you think there are volcanoes somewhere else? Okay, so everybody must think all the other planets like form from quartz. Okay, it turns out this was a trick question, actually. Actually, all 3 of these exist everywhere in the local universe, and they are common components to building planets. So these are tiny building blocks. So essentially, these sand floats around, they collide and attract each other due to gravity, and they keep on colliding until they get to meter size, in which there's still a mystery of how they get to the meter size. But once you get beyond that, it's relatively simple to collide 2 pieces of rock together to form larger rocks. And when colliding, there's so much heat and friction that's going on. Those energy melts the interior. That's how you form the interior of planets. And then it slows down and it cools down and it starts to form the structure of terrestrial planets like ours. So.
How do you know all that?
We don't know all of that, actually. That was.
But how do you know these elements are there?
So actually.
Like olivine?
Yes. Oh, you can tell the rest of the story.
No. How do you know?
Okay, so if you look at the top right picture, that's taken actually not with us, but with James Webb Space Telescope. So we look at particular features in the infrared. So we would want to look at regions around 10 microns, 15 microns, and 23 microns. So those bands ratio can tell us if there's something that's characteristic of olivine emitting there. But of course, we also would like to use spectrographs to more deterministically say that this is olivine.
Okay, so you take images first and then you follows it up with spectroscopy.
Yes, that's the usual way, but you could also just go say, I'm very confident I want to do spectroscopy just to be sure. And I don't think it's big enough to make a beautiful image like this.
So you get chemical signatures in both in the images and in the spectroscopy itself.
Yes, spectroscopy usually confirms the chemical signatures, and the images give you clues. Thank you for helping me clarify that.
Yeah.
It was-
I don't take anything at 10 microns, so I know nothing about it.
So actually, ground is not a very good place. Gemini used to do 10-micron imaging back in the old days, but now it's more frequently done in the space. BLT still does some of it because space doesn't have the thermal background from our atmosphere. Turns out our atmosphere also glows at 10 microns. So there's a lot of emission there. So it makes pulling out the signal very hard from the atmosphere. Yeah. Okay. One last picture is, I thought it was funny because I like drinking coffee and making latte art. This is a special edition I made for just to make fun of when you have bad focus, what happens. And so on the left-hand side, I tried to make the latte art with soy milk powder, which doesn't stay very nicely. I made an analogy to Hubble, because before the mirror correction, the images are fuzzy. And after...
Do you guys know Hubble? Like the telescope? Yeah. You know, it was like not very in focus at the beginning. Okay, it was like terrible in the beginning, and people were like, oh my God, we spent like 20 years and like this is the result and it's terrible. And they had to like send people up there to correct it. Like a guy named John Grunsfeld went up there and actually like fixed the mirror. And then it worked. And that's why you guys know it now. Otherwise, we would just be
Contact
space.
lens.
What did he do? Did he added a lens?
He was a very big contact lens.
What?
Okay, all of you guys know more than about a mirror correction than I do. All I know is it's fuzzy. And then I made it again. I tried to make it a little clearer, which is on the right hand side using a different kind of stereo. So comes up. A little hobby.
Oh, cute. Okay, thanks, Cicero. All right, you guys are not off the hook, so we're gonna go around and just quick introductions. Just say say your name and like just basics about like where you're doing your internship and yeah, what you're doing for your internship. Like, just a couple sentences. We'll start with you, please.
Hi, my name is Karina. I'm interning here at Gemini. And my project is to prepare models for a 3D simulation of the telescope.
Hi, my name is Min. I'm interning at Subaru Telescope. My project is upgrading software for MAROON-X instrument, mass design.
Okay, for the spectroscopy for marks. Okay, nice. I use marks all the time, but only for imaging. Yeah.
Hi, my name is Danny, interning at IFA, but I'm going to be monitoring the Subaru spiders to correct for low wind effect.
I'm Shade. I'm also at Gemini. I'll be working with Karina, so she's pulling the models, and I'll be making the 3D simulation in Unreal Engine of the telescope.
My name is Tristan. I work at the Subaru telescope. I'm upgrading the power system for the prime focus of the Subaru telescope's instruments.
Hi, my name is Georgian. I work for the Subaru telescope. My project is basically designing the readout for the accelerometers to measure the vibrations on the telescope and then put that into the Skexeo adaptive optics system for like a control loop.
Nice.
Hi, my name is Christian. I don't intern at the telescope. I intern at the Professor Winston's basement. I don't work with astronomy, but excited to learn things. I actually work with in the computer science part, NLP. So NLP stands for natural language processing. Process certain languages. Mainly his focus on the Hawaiian language because we're here in Hawaii. And yeah, excited to just learn about astronomy things.
You guys have any like astronomical component of what you're doing? Is there any interface or do you pull any code or?
Sometimes when your code doesn't work, it looks like stars and you see stars. So maybe that's
The delirium is still.
It's still really
Yeah,
there, yeah.
okay.
Delirium and hallucinations very much.
Oh, hi, I'm Winston. I'm a professor of computer science at here at Hilo, and I do natural language processing and machine learning stuff.
My name is intern here at Gemini Observatory. Yeah. And for my project, I'm making a project knowledge management system, and it will integrate large language models to the database.
I don't know what any of that means.
You ever you
Sorry. I work here and I don't know what any of that means. It's gonna help at some point for stuff. Okay. Yeah.
I mean, you can like you can. Sorry, I can't explain it all right now.
Okay. Who are you working with?
Patrick Parks.
Patrick. Okay. Yeah. Yeah. I don't know what Patrick does. That tracks. Okay, sounds good.
I'm Cassandra. I'm an intern at the USDA. I'm working with bug tracking.
Nice.
Yeah. I'm Sylvia. I'm also interning at Gemini. Cicero is my mentor. And for my project, I'm building 3 different neural networks to predict certain stellar properties stars that are likely to host exoplanets.
I'm Noah Martinez. I'm working over at IFA with David Jones, and this summer we're looking at supernova feedback in merger systems.
Deshaun, thankfully, I mostly no longer work, and I'm just here for an observation.
Nice, welcome. Okay, thanks, guys. Let's see what's going on with the telescope before we get back to that. So I think what I understood is we are on target. So Adam measured locations of the stars in the guide boxes, and they are tracking right now, and they are integrating. So let's see if I can get over to our screen.
Yeah, we got 5 minutes till the first image reads out.
Cool. So this is our we call SecExec, so sequence executor. This is the interface that we use to start and stop observations. And so it's a web-based tool. I think I'm in non-interactive mode. I hope so. And so Adam has just started a 1180 second exposure. So near 20 minutes. And this begins or continues this program's observations of this particular target. So you can see over on the left here, this is step 31. So I mentioned earlier this program is asking for 6.5 hours of observations. So that requires a lot of different steps. For any astronomical observation, as I'm sure anybody that works at the observatory knows, there's a lot that goes into it. Basically, you want to take out, like, for example, that you have shake on the telescope, right? So you have wind that shakes. We have an instrument that I'm partially in charge of called GNears. It needs to be very cold, and it has kind of antiquated pistons on it that keep it cool. And so it actually shakes the entire telescope structure. It's pretty loud too. And so it causes vibrations for all the other instruments. And so you have to somehow model that out, or you have to put in some sort of like either electronic mitigation or mechanical mitigation in order to not have your image move back and forth, right? Because again, 1/3600th, 1/10 of 1/3600th of a fingernail is the precision that we're going for. And so when you have giant 3-ton instrument shaking back and forth on this 80-ton structure, that can cause some issues. And so like SCEX-AO needs even higher precision. Have you used SCEX-AO before?
No.
No? Okay. But it has a coronagraph. It's an instrument that looks in the near infrared. It uses adaptive optics. So it basically corrects for the turbulence of the atmosphere and of the ground. And so it takes in, so on a given night, so Adam, what's the seeing tonight? 0.4 roughly?
Yeah, 0.4, then jumped up a little bit, but that's coming back down. So I just did a measurement of that galaxy image we took. It wasn't fully stabilized, but I believe we were getting around 0.8, corrected around 0.7. I
Okay.
think it's probably around 0.6 average, about where we were.
Nice. Okay. So yeah. So the quantity that Adam was just talking about is seeing. That's basically a way of determining if you have a point source in the sky. So let's say a star. So star is big, but it's really, really far away. And so the angular diameter of the star is basically infinitesimally small as we see it from Earth. So it's a point source. But when it hits the atmosphere, when the light from the star hits the atmosphere in these plane waves, it gets scintillated, so it moves around because the atmosphere is moving. So there's all sorts of different layers of the atmosphere, all different chemical composition. It scatters the light. And so this is why you see stars twinkling. But thanks to a program in the 80s that Ronald Reagan, who knows Ronald Reagan? Anybody? I'm sorry. And so the Ronald Reagan started called Star Wars. It was a program basically designed to shoot down spy satellites. So this was back in the day when we wanted to do that sort of stuff. Now we're much more obligated. And so this program never worked. It was declassified, and it turns out that lasers aren't great at shooting down spy satellites. But what they are great at is creating fake stars. And so what you can do is you can so for example, for Skexeo on Subaru, generally you're looking at a bright star, just like Cicero showed. You have a bright star, and you're looking for the planetary disk around. So you have a lot of light coming from that bright star. You can add a laser if there's not enough light to make a secondary fake star, and you feed all that information into your telescope and into a computer system, which makes corrections roughly 1,000 times per second of this little mirror, deformable mirror that's about this big. So in our last Shadow of the Scientist session was on Skexeo. We saw the deformable mirror in the lab, and it's about this big, and you can see it working. So there's 1,000 signals per second. You see it just vibrating like that, and it's making a composition correction for the plane waves being distorted by the scintillation in the atmosphere. So it's basically counteracting the atmosphere. And so what we see on this observation tonight, we're not using adaptive optics. And in fact, we're looking in the optical, and currently no technology exists to do adaptive optics in the optical. Adaptive optics works because you split the optical and near infrared light, and you dump all well, actually Skexeo works a little bit differently, but most adaptive optics systems work where you throw all the optical light to this measurement system, and it measures in real time the scintillation of the atmosphere, and then you make corrections for the science light, which is the near infrared light. And so we see 0.6 arc seconds, so a point source in the sky right now is 0.6 arc seconds, so 1/1800th of a fingernail. Adaptive optics can do better than the James Webb Space Telescope, than the Hubble Space Telescope. You can get down to 0.05, 0.1 arc seconds. Actually, even without adaptive optics, if you look far enough in the infrared, so like where Cicero is looking, the natural seeing can actually be, the atmosphere is a bit more calm there. So you can actually get down to about 0.1. We actually beat James Webb on your first observations with G-nears, just because she was looking so far in the infrared that the atmosphere was calm, and we were able to see near diffraction spikes on the telescope, even without adaptive optics. So yeah, this is measured. So Adam is like constantly measuring this at nighttime, because as I mentioned before, the way Q observing works is that the science team makes a specification for what the conditions they need. And this seeing value is really, really important, because you have these slits in these slit masks that are a certain width. And so you can imagine the broader a source is, so if there's a lot of turbulence in the atmosphere, a lot of turbulence on the ground, it's going to blur out the light. And if you don't have a correcting mechanism for that, like adaptive optics, you have your narrow little slit there, you're pushing more and more light outside of that slit. And so the object is going to become dimmer and dimmer as you measure it. And so this is, I think Adam's showing on the screen right now, a measurement that he made of the alignment stars that are in this mask. So these stars that are just sitting in the boxes.
Yeah,
And-
I just was gonna show, yeah, this is just a really good image of good signal of a full with half max. So this is basically a profile cut of the star of the image. And this is how we actually do the measurement, is we do a cut across of the pixels and look at the signal amount. So the light gets broken up by the atmosphere and gets broken up naturally into a Gaussian curve, like a bell curve. And the worse the atmospheric conditions, the more it spreads out and the peak actually lowers. So the same amount of signal will come, same amount of photons, it just gets spread out more. If you think of it like going on the other side there. I can do a radial profile here, you sort of see. Right. So what we do is we take the measurement of that, of the centroid, the center of that star. And we do either what's called the half flux diameter or full width half max, which is you measure the distance out if you take half of the flux. So like basically if this is the flux, half of this, go over here and do something like that. It does some other things too, but basically we use that measurement and we basically it's in pixels, and then we have to do a conversion. And adaptive optics basically, you send the laser up into the sky. A circle is supposed to look like a circle, so if it looks like a square when it comes back, you can correct that. So you just basically correct for that. And if you know how to correct how all this stuff is distorted, then you apply the same corrections to the star, then you're basically making the star look better. Because the same thing that's happening to the laser that's coming back, what you're seeing, the laser that you put out there coming back is happening to the stars, right? So that's the lovely thing about it. We shoot these lasers up about 90 kilometers up, and into a very, very small sodium layer that's created by micrometeorites. And just a very, very small layer. Actually, Keck is lasing tonight on occasion through these clouds.
Yes, in fact, Adam, I had my hand raised because I was watching Keck laze in real time and wanted to share it with you, but I can share as soon as you're finished. They're not lasing right now, but I moved the timer back so we can see them lasing.
Also, I can't see your hand raised, so you just have to yell at me to stop talking to.
Are they poking holes?
Yeah,
into
same
the
for us,
clouds?
Jamaica.
Okay, all good, no worries. I will.
Yeah, so this
I'll
in this
follow
image
that.
here, this is the Keck-2 telescope, and so I guess it was Keck-2 that was lasing. You were seeing it in this in the screen.
Keck 1.
It was Keck-1.
Yeah. I'm going to share my screen, Brian. I can
Yep.
show it. I'm on Astro Asahi Live. If you all are not familiar with it, it is a fantastic site to use. It's on YouTube, CFHT camera. So this was about 15 minutes ago, and you can see just how powerful this laser is. And that is Keck, yeah, Keck 1, right?
Keck-1, yep.
Yep. So you can get to see that laser in action, and I'm going to current. Yeah, so they're no longer lasing, but when you were talking about it, the laser was on, it was spot on, it was perfect. So I'm glad I got to share that. All right, I will stop my screen share. But I will say the Astro Asahi Live, there's so much that you can observe happening in real time by the observatories on Maunakea with this channel. So Cicero and Brian can make sure you know that link, or you can just talk to me after because it is amazing.
Yep.
So you can see Keck's laser in our top end camera there. If you share that screen again. It's very faint, but see
Say it again now.
if you share your the screen that you did earlier, you see the top end camera, you can see Keck just turned on their laser again.
Ah, yep.
And you can see the laser in our field of, well, it's not near our field of view, it's crossing above us right now.
Yeah. So it was right in here. If you guys can see that, just at the edge there, the up camera. That was the laser there.
Oh, I saw.
They're actually doing engineering night tonight for the OSIRIS instrument, so I'm sure they'll be back lasing again.
Oh, yeah.
They're doing it all the way up until midnight. Okay, so let's you guys have any questions?
Can I ask, like, in the operations room, like, as you're telling the telescopes to move, is there like a noticeable delay between input and execution?
Jenny, did you hear that? Do you
What?
have time to potentially answer? So the question was, when you send a demand to the telescope, is there a noticeable delay between that demand and the actual movement of the telescope? And like, how quick is it to move in general, the telescope?
A second and a half sometimes. I want to press all the buttons one after the next very quickly, but I have to wait for it to get the command. Yeah, it takes about maybe a second to a second and a half per button I'm clicking through the TCC.
Yeah, and I mean, she's controlling the telescope on Maunakea with stuff there. So the software it's mimicked in our summit facility, but I mean, it's sending signals up there. So actually,
Sometimes it complains and it says that it's upset with me because I pressed buttons too fast. So I have to control myself and allow it to receive what I'm telling it to do.
Yeah, you have to realize that all telescopes, even the ones on Maunakea, they sound cool and fancy, but in reality, they were designed starting in the late 80s and the mid 90s, late 90s, and started to be built in the late 90s and got on sky in the early 2000s, right? So a lot of these telescopes are using technologies that at the time were new, brand new, and are now pretty antiquated. And it's really hard to try and upgrade telescopes because the technologies are just so different and it's hard to get spare parts for things. So whenever we do upgrades or do software changes or change it to a different operating system like we did a couple of months ago, it's months of planning, preparation, testing, things like that, just to make sure that things work properly. I mean, this was like a year in advance of us trying to roll out operating system. And yeah, if you click too fast, it can ruin your night pretty quick. So you just have to let it go, just flow with it. That's the first thing we have to train operators is just click. It's okay. Take your time. No worries.
Take your time. Also, different telescopes, they will have their software designed by, in-house people, which can be nice. Or they'll get the software designed by somebody outside, and those are tricky because they have to like kind of have a package already available with the initial release that says once we release it, we'll come back and we'll fix all the things that we didn't do right the first time or the second time. And, that has to be within a price range that they can afford, because when they have their final product, you might not have anybody to help you fix things. And you're just dealing with them now for the next 5 to 10 years, whether or not it's working exactly right. And anytime there's something that has to be built, they're looking at, you know, is this company still gonna exist in the next 10 years when a part breaks? Or we need advice?
Yeah, Brian can definitely get more into this with his experience with instrumentation, you know. When we plan for instruments, new instruments, they're usually built either by a group or they're headed by a principal investigator or PI from some academic institution, or they might be built by the academic institution through grant funding, things like that. It's all public funds. It's not private money. So it has to get vetted, it has to get planned well in advance, you know, there's a lot of planning involved. And in that time period, if you rely on your graduate students to do all the planning for you, all the work for you, they're gonna go. They're gonna go elsewhere. So if you're relying on them to make the software, they leave. Yeah, so we've had that a couple times, you know, where we were like, oh man, we need to update the software. They left, you know. But you know, that's the nature.
Yeah, just to give you guys an idea of timescales. So the prime focus spectrograph, anybody heard of that? Anybody at Subaru heard that? Prime focus spectrograph? So this is like a super powerful new spectrograph that came to the Subaru telescope. Let's see what the first nights were, like 4 months ago on Sky. The prime focus spectrograph takes a spectra of 2,400 objects at once. So the Gemini Multi-Object Spectrograph, at best, probably can do about, if you really push it, maybe 60 objects. You can do this like special combination of the slip mask and a narrowband filter behind it, and so you can maybe get that to like a couple hundred, but you get very limited information. The prime focus spectrograph does 2,400 objects at once. So it's the most powerful spectrograph on the planet, like bar none. The initial designs of this spectrograph happened 20 years ago. And when I was a postdoc in the south of France, Marseille, in 2011, they were starting the initial fabrication of some of the parts. So 14 years later, after the first parts were built, the instrument finally goes and starts taking astronomical data. And so the technology that's encoded in that instrument was conceived 20 years ago and start actually input into the parts about 15 years ago. So you're always lagging behind, and there's not like many prime focus spectrographs on the planet. There's one prime focus spectrograph on the planet. So it has specialized parts, and if it breaks, you probably are going to have a hard time finding a replacement. For some of our instruments, we have to go on eBay to get replacement parts. So yeah, our adaptive optics system, people are fishing on eBay for parts. And it's like, yeah, 1980s, 1990s level technology. Still works-ish, but yeah, it's getting harder and harder to find parts.
Now, Brian, didn't you recently use Subaru's prime focus spectrograph?
I did, yeah. It was the first night ever on Sky. My research group was there taking data. So we're still trying to get those data reduced and in a form that we can use scientifically. But that process, you can imagine, is very, very difficult. It's just this immense amount of data that all comes at once. And so the prime focus spectrograph looks all the way from about 400 nanometers to 1.2, 1.3 microns. So it has this huge spectral baseline on top of looking at 2,400 objects at once. And actually, you could only pick about 1,600 objects that you're interested in, because 800 of those fibers, so the F is, well, sorry, no, but it should be. So it's 2,400 fibers, 800 of those fibers are for calibrators. So 400 are for stars to measure the absolute throughput of the spectrograph, and 400 are blank sky, so that you can basically measure the emission of the sky and subtract that off from the science data. And so it's an immense undertaking to get those data in usable form. And like for any astronomical observation, not only you have to take out the shake and all the, the wind shake and all the terrestrial things that are happening, but anything coming from the atmosphere. So Cicero was talking about looking in the infrared. The atmosphere actually glows. It glows not only in the infrared, but in the optical as well. You get bright emission lines. Let's see if actually we have a science spectrum coming out.
Yeah, and there is emission in it. If you want to, I'll bring.
Yeah, perfect. Right on cue. Yeah, so this is a raw frame. This is a raw frame that Adam just took of the globular clusters in this nearby galaxy, and by nearby, probably 10 million light years or something like that. Ooh, there's a good combination there. So these circles here actually come from the galaxy itself, or the globular clusters. So these are emission lines from certain elemental transitions. I recognize this pattern, so I think I know what this is. So this should be an emission of hydrogen and then doubly ionized oxygen. And so this actually comes from an astronomical source. But if you look in all of these, so each one of these is one of the slits that you saw in the slit mask. You see these vertical lines. This is all emission from the sky. So this is effectively terrestrial emission coming from the atmosphere. And so that's not what you want. You want to get to the intrinsic properties of the source. So you want to remove the fact that you're observing through a telescope. You want to remove the fact that there are high energy particles slamming into your detector. So that's what these things are here. These are cosmic rays. You want to remove the fact that the atmosphere is emitting. You want to remove any shaking. You want to remove the fact that you're viewing through a slit, that your optics are imperfect, so you don't reflect all the light that you receive. You want to account for the fact that you have a finite diameter primary mirror. You have to remove all of these things. And so some of this is done through models. Some of this is done from first principles through mathematics. And so in this case, we have a slit spectrograph. Oh, I was wrong. No. So that set of emissions is hydrogen alpha. So it's one that's from hydrogen, and then singly ionized nitrogen and singly ionized sulfur. So that's these lines here. And then that's oxygen, I think, one. And so in a slit spectrograph, you actually have the sky and the target together. So Adam, do you mind zooming in, like right in the middle there where you see the emission lines?
These, yeah.
Yeah, so, yeah, perfect, thanks. So in like centered up in the frame here, you can see like a kind of faint horizontal line, and then these circular emission features. That faint horizontal line is called the stellar continuum of this source. So this is just aggregate emission from a bunch of stars all together. This emission here is from gas surrounding those stars, probably. And then the remainder of the slit is just empty sky. And so you can measure at that precise location the sky emission. You can, so in that slit, you can use that to inform a model. And then you can subtract that model off just of the sky emission. And what remains is the emission from the stars and the gas. And so that's great. In a fiber spectrograph, you have a circular aperture like this. You have a fiber optic cable. You have a circular aperture, and you're just dumping all of the light together. And so you can't spatially resolve anything. And so you have to have dedicated fibers that give the sky emission, and then you basically average those together, and you get a sky model for your source. And so now, yeah, please, Adam.
Actually, did you like that data? I mean, before I move on, since we might pull it out tomorrow. Talk to me after this, or actually now. You got QC power. I set the data that usable last night because I wasn't a huge fan of it. But it looks bit similar tonight, but if you think that looks pretty good, I'll just go ahead and send it pass.
What's
Data
the
analysis on the
specifications and
spot.
what's,
Huh?
sorry, what's that, Jenny?
Data analysis right on the spot.
Yeah, man.
STS.
What's the specification? What does it require and what are the current conditions?
We are IQ 20, borderline IQ 70. It is CC. It is IQ 85, CC 80, and we are definitely CC 80, CC any mix.
I would throw it to the PI. It looks pretty decent to me, and I would guess they're probably getting more signal than they would expect given the constraints.
Last time was worse. Last time was definitely way worse. But yeah. Anyway. All right.
I think that's borderline IQ 20, IQ 70 is a big deal. So even if it's a little bit extra cloudy, I think it's okay.
Yeah. This might mean nothing to y'all, but the last couple of nights have been super frustrating for me as an observer because we have some of the rare kind of combination of conditions that we typically ever have, which is really good seeing, but terrible clouds, and nobody plans for their programs to be, good with clouds and with seeing. If you have a program that allows for, a flux extinction of like 2 magnitudes, that means like you're probably looking at something very bright. So if you're gonna look at it, if you're looking at something like really good seeing, that means you're concentrating all that light onto the detector as well, because it's all you get in the same amount of photons just in a smaller location, which means that the signal gets stacked up, which means you can have saturation, which once that happens, the science is not usable, or we can't use it for science anymore. So you have this balance of like conditions that you have to play with. So I'm trying to make decisions on what programs I can violate the constraints that were agreed upon because the seeing is better, and make these kinds of trade-offs. It's very weird, but these are the decisions we have to sort of make on the fly. It's strange, but it's my last night. So I'm happy to not have to do that tonight.
Okay, so Adam, if I just check if we're in SP 20, which we are, CCNE IQ 20, they're basically getting nominal signal to noise. So that would be the same signal noise as CC 80, IQ 85, and we're borderline CCNE, CC 80, right?
Yeah, I haven't used the ITC or anything.
Yeah, so that should be better than nominal signal. So I think we're safe.
All right, cool. Okay, now where to go? What to do?
Now, Brian, you all
Yeah.
were using some terms CC and IQ.
Yep.
What is that?
Sorry.
Yeah, I'll back that up. So, yeah, so there, so we can't plan for every combination of conditions, as Adam said. We try hard. We basically have 4 to 5 different constraints that we look at, and this is where we break up these different condition constraints into quartiles or percentiles in some way. So the 2 things that we were just talking about, actually 3 things, was IQ, which is image quality, which is another way of saying seeing. Seeing actually refers to the atmosphere itself. Image quality refers to the optics plus the atmosphere. So image quality is just very basically, you have a point source in the sky, how much does that blur out into?
Think of it as like that galaxy, that image. some people might be okay, like if they're getting a spectra of the galaxy, they might be okay with the IQ to be, you know, worse because they're getting spectra. But if you're getting a really pretty picture of it, you want the best IQ that you can get, like IQ 20 is some of our best conditions. So they might put in IQ 20 for their constraints. And so we wouldn't be able to observe it in any other constraint except for the best seeing possible, because that's what they want it for.
So when the numbers lower, that means better conditions. So IQ 20 refers to the 20th percentile best image quality on Maunakea, or better. And in the optical, that's about point, depending on where exactly you're looking in the optical, because the image quality changes as a function of band. It gets better in the redder bands. So if you go all the way to the crazy places that Cicero observes, it actually gets quite good, as I mentioned earlier. But it's about 0.55, 0.6 arc second seeing. That's kind of the borderline for IQ 20. So if it's better than that, and that's really good, then those are some of the best conditions that Maunakea gives. And just for an example, like
especially like 20% of the nights on Maunakea in a year are that seeing or better. Yeah,
exactly. Yeah. So if you temporally sample Maunakea seeing over the entire year, 20% of the time it's going to be that or better. As I said, I grew up in California. We used the Lick Observatory when I was in grad school. Does anybody know the Lick Observatory? Yeah, the university, actually UC Santa Cruz helps run it. And so their typical seeing conditions are, well, I don't know, when I was there anyways, typical seeing conditions were about 1.5 arc seconds. So they're good seeing. If you got there and the seeing was like 1.2 arc seconds, you were happy. And so Maunakea being the best observing site in the world, it's better by a factor of 2 on average than at the Lick Observatory and then at many other observatories. So generally exceptional conditions on Maunakea. But still, some programs require the best of the best even. So that's image quality, IQ. There's CC, which is cloud cover. So right now, the clouds are actually not so bad, kind of going in and out. But so CCNE, CC80 were the 2 terms that we were throwing around. CCNE and measured over here. This is measured from the Canada, France, Hawaii telescope. This is a kind of rough estimate because of the way that they calculate it. But it's measured in magnitudes of extinction. You guys know the magnitude system? They teach that at the USDA at all?
Oh, like absolute magnitude?
Like absolute magnitude, yeah. Yeah, you know that one? Okay. It's a measure of brightness. It's a really messed up measure of brightness. So it's when things get more negative, they get brighter in the system. And a factor of 2.5 in magnitude corresponds to a factor of 10 in brightness. It's a logarithmic system.
So yeah, and in terms of operations, we think of it in terms of flux or counts. So we do lots of things in operations at night in real time by looking at the counts, the signal counts in real time. So we're looking at our signal counts drop. And if we lose a certain percentage, then we know that the flux has lost a certain amount, and we're now that the clouds have gotten that much worse. So yeah.
So you can see the crazy ride that they've been on right now. So on the bottom left here, these are our strip tools, and these show various measurements that are very helpful for both Jenny and Adam. And so this WFS, this is wavefront sensor. They're using the on-instrument wavefront sensor for GMOS. So this was this little red thing that I was showing earlier in the DSS image. So going back down.
Let's go to Q30471, hydrants 2.
Okay, so we're moving on to another target. But so this is the wavefront sensor. It's measuring the guide star. And you can see as the clouds go in and out, so this is just measuring counts per second. And so you can just see it just fluctuating up and down. The brightness of the star remains the same, but the clouds obscure the star flux. And so it causes a drop in counts. And so this is measured both by the wavefront sensor and by other observatories. And so we get an estimate of how serious the cloud cover is and how that's affecting the observation.
Serious it is. Yeah, and for infrared instrumentation, it's okay. Like it's not that bad. But for optical stuff, it's sensitive.
Yep. So so we also measure, we don't measure it, but we use the amount of water vapor that's in the atmosphere. This is measured from the James Clerk Maxwell telescope and the submillimeter array using radio frequencies. You can measure the amount of water vapor in the atmosphere. So this is important for near infrared observations, especially for observations like Cicero takes. So you don't want a whole lot of water vapor there because it basically causes very bright sky emission and obscures your astronomical target. This is a measurement of image quality again. These are all measurements that have to do with things that are important for the telescope and telescope safety. The other thing that I mentioned earlier was SB. So SB20 is the term that I said, and that's surface brightness. So right now the moon's not out. The moon is at 5% illumination. And so the moon causes, well, it's very bright in the sky and you're looking for something that is usually very, very faint. So like the faintest star in the sky that you can see with naked eye from, let's say, from Haleakala, that's 6th magnitude. Yeah, it depends on your seeing, but about 6th magnitude. The things that were the brighter things that we're looking at. So just compare like full moon brightness to the faintest star that you can see. Okay. The faintest things that we're looking at with the Gemini telescope or with the Subaru telescope, these are going to be roughly 20 magnitudes fainter. So 100 million times fainter than the faintest star that you can see with your eyes. So you can imagine the moon, being what it is, super bright, is going to affect your ability to see those things that are 100 million times fainter than the faintest thing that we can see with the human eye. And so that's important when we take our observations. Is the moon out? How close is the moon to the target that we're looking at? And you put those constraints in ahead of time. So water vapor, surface brightness, cloud cover, image quality. And the last thing that we look at, very broadly speaking, is something called air mass. You guys know what air mass is? It's the amount of atmosphere that you're looking through, basically. So it's telescope can point directly up. And when you're looking directly up, you're looking through the least amount of atmosphere. When you're looking on the horizon, you're basically looking at it's like a tangent on a sphere. You're looking through a lot of atmosphere. And so, I mean, you can see this when you go out at nighttime and look at the stars, if you're not in Hilo, because you can't see stars in Hilo. Straight up, stars not twinkling very much. But if you look on the horizon, it's twinkling a bunch. And remember, the atmosphere causes the scintillation, the twinkling of the star. And so you look through more atmosphere, more scintillation occurs. And so if an object's up here, you're looking through less atmosphere, you're going to get less of those emission lines, less atmospheric emission, so you can see the astronomical target better. You're looking directly on the horizon, it's much harder to see that. So it's going to get more blurry, the atmosphere is going to get brighter, everything's going to become harder. And so we generally try to stick roughly above 30 degrees altitude. So roughly like this. We prefer to keep things up near, well, not totally at 90, but 70 to 80 degrees. Technically, our telescope can actually point down to 19 degrees altitude, so we can, which is helpful for the things that are right near the pole star, right? Because we're at effectively 19 degrees latitude, so the pole star is at 19 degrees altitude. And so, but we generally try not to do that unless we absolutely have to.
Yeah, smaller telescopes, actually, when I first observed my first ever observing program, we looked through air mass of 3, which was IRTF, which is a smaller telescope. So for smaller telescopes, it's a little more flexible to go down closer to the horizon because they don't have to worry about demerging over and destroying it. So Yeah, the signal to noise was not that great, as Brian was mentioning, because you're looking through a lot of atmosphere. Nonetheless, the star is really bright. It's 3 magnitudes brighter than the naked eye star, the faintest naked eye star, which makes it doable in that extreme condition.
Was it the same target you looked at with Gemini?
No.
No, okay, because that was like second magnitude or something, right?
But it's overhead.
Yeah, that was overhead. Cool. So that's basically what Adam's keeping an eye on, and we always try to optimize the programs to get them, up in the sky as much as possible. So this chart here.
If you want to watch me acquire with Flagrants too,
Oh, okay.
I'm not gonna mess it up this time.
Well,
I can't guarantee that.
We believe in you, Adam.
Thank you. I
So
messed
this
up
chart
last
here-
night and lost some time because I forgot to center it properly. I haven't used this instrument except maybe once before. But I think tonight I will be using it a lot if I'm staying in this program.
Yeah, it looks like nonstop. You get plenty of practice for the rest of the night, Adam.
Yeah.
Yeah, that's what's
so-
tricky about observer side. There's a endless amount of information to know. And then you only touch that job once every month or less. And you have to kind of just sit right back in the seat and make it all happen, without, maybe you have like somebody working on the other side of the room that can remind you of things here and there, and manually can refer to, but a lot of it you're kind of just recalling on the fly.
Technically, I never got trained on this, now that I think about it.
Yeah, he never got trained on that instrument and he's running it right now with
It's just like anything else.
an instruction manual.
Yeah,
A lot of, I mean, it's obvious. Near infrared spectroscopy.
It's pretty obvious. Yeah, it's
activity.
like any other thing.
Yeah, I mean, you put it in the
yeah.
sled, it's fine. But I mean, it raises an important point. So one of the things that Gemini is really awesome at is we have all of our, effectively all of our instruments on our support structure at once. So for all his talk, Adam perfectly centered up the target on the slit. There it is. So this is the iGreens 2 slit viewing camera. So iGreens 2 is one of our 4 instruments that's on board Gemini right now. Cicero, do you want to talk about what iGreens 2 does since you're on the team and I'm not?
Oh, yeah.
It's the one
Right.
instrument I don't support.
Oh.
Yeah.
Right, I didn't know.
Actively support. I still support it.
Okay, so this is a near infrared instrument. So it looks at wavelengths that goes from about 1.25 to about 2.5 microns. So those are J, H, and K bands. So these are more red than the reddest wavelengths than the GMOS instruments, which if dynamic wavelength is probably like 1.1 wideband.
Yeah, if you're really
1.1
pushing it,
microns.
yes, yeah.
So these look at infrared, if 1.05.
Let's be honest here.
So this instrument, it has a very high precision. So it, as Brian was talking about, how astronomers love spectra because it gives you all the elemental information that any astronomical object could contain. This splits the light in such detail that it has a resolution of 45,000 as compared to the highest resolution of GMOS, which have a resolution of about 5,000. So that's a factor of 9 better. So that means every line you see that Brian and Adam was showing on the screen, you get stretched 9 times more apart, and then you can resolve even finer details. So I have to say that this is one of my other favorite instrument other than Genius, which Brian is an instrument scientist.
So nice of you to say.
Because one particular use of this instrument is that you can measure clouds and atmosphere on other exoplanets. So planets outside of the solar system, we now have the ability to look at carbon monoxide, carbon dioxide, and water on those atmospheres. And so the way that it's done is, how many of you guys are familiar with Doppler shifts? Or okay, fair amount. So like a fair amount of you guys. So basically, as a planet goes around its star, they have a common center of mass, right? So they go around the center of mass, common center of mass. So the net effect of that is the rainbow gets tucked left side, right side, like around different wavelengths. So that creates a shift in the tiniest feature in the spectra. So I guess you have a, okay. Oh, Brian's probably looking up an example to show. But that tiny little shift can be resolved by such a fine, high resolution instrument in the near infrared. So as a planet goes around its own star, it has summer, winter, right? And as in summer and versus the winter, these lines will be at different locations, usually opposite locations. So you can go and measure these with this instrument. So that's the reason why I really like it as someone who studies how planets around other suns form. Okay.
Brian, before you show your screen, can I show a quick image of the CASI team standing underneath the telescope with
Yeah.
IGRIN behind it?
Yeah,
Because
please.
it's a great image. I think it really gets to show the scale. And so IGRINS 2 is this yellow box here, and you can see the other instruments here mounted, but please go ahead and tell us more about this image.
Yeah, so this image is, so I wasn't actually, were you here for this?
No.
No, you weren't in the picture?
No.
Even though you're on the IGRIN 2 team?
I think this is the development team, the instrument, not the operations.
Okay, I think K1's in that picture. So anyway, so this, so for those of you who've been to our summit facility, you'll recognize this, but this is just like sitting under this 80-ton telescope. So it takes a lot of faith to sit there. And this is the Korean Space Agency. So they were the ones who built this instrument. And their team came over to do the commissioning. So basically to make sure that everything works and to make all these precise measurements to determine the properties of the instrument itself. The thing behind them, so I'll just get up there, all this stuff here. This is what I was just showing before. This is our instrument support structure. So Genius actually is this one right here. Over on the side
Cicero, can I get you to come to the control room real quick?
Oh, me?
Yeah.
Okay.
Yeah.
I'll also bring back the.
Tamika, you can keep sharing the screen.
Oh, do you want me to keep sharing that screen? Sorry.
Yeah.
Okay, I'll go back to sharing that.
And my guess is that this is, I'm not totally sure, but I'm guessing this is IGRINS 2 here. It was originally at the very bottom of the telescope. This is also where the MAROON-X instrument sits. Now IGRINS 2 is sitting where Genius is, because Genius is in our summit lab being refurbished, let's say. So it's getting all of its parts redone. And so they came for 2 weeks to do like a first light, so first scientific light to the instrument, and then to make all these really careful measurements. And so actually when we switch instruments, and this is the same for effectively every telescope, so this is the easy one because this is a cast focus. So you have to take off this entire 3-ton instrument and replace it with the 3-ton instrument. And so we do these instrument switches once every couple months now, because it's just so demanding. And for like the prime focus instruments, which are at the very top of the telescope, it's even more complicated because you either have to go to the top of the telescope and actually take a crane and take these things off and put it back on, or you have to turn the telescope down towards the horizon and then try to switch things out. But that creates weight imbalances. So, yeah, so this was a celebration that everything works. This is, I think 10 years of work that they did to make things happen. We have about 10 minutes left. So I'm wondering, you guys have any like burning questions about, I don't know, operations or something you want to share about difficulties that you've had in your project or concepts that, I don't know, may be relevant for your project?
I'm curious if like we're talking a lot today about like observation conditions, and I'm curious if like a telescope like Hubble has a unique set of constraints since it's not on the ground.
Yeah,
If you might think about that.
No, it's a great question. So, Hubble, and even like James Webb. So Hubble's around Earth's orbit, right? And so this is how we were able to send John Grunsfeld up to to service the telescope many times actually. But the James Webb Space Telescope, for example, is at something called L2, the second Lagrange point. But both of these are bound to our orbit, to Earth's orbit in some way, right? And so there's still seasons for these telescopes because the sun is in a particular location relative to the background stars, right? And so we see that with the changing of the stars in different seasons, right? And so same thing in space when you take the observations. The James Webb Space Telescope or Hubble, when it's looking at infrared, cannot look anywhere near the sun. And in fact, it has to be at certain angles with respect to the sun in order to keep its thermal properties, because even very, very slight changes in temperature cause expansion or contraction of the optics. And like the level of precision that we need for our optics is somewhere, depending on which optical element, is somewhere between a micron and a millimeter of precision. So so we can keep things like kind of, there's a lot of thermal inertia these things, the telescopes are huge, the instrumentation is huge, and we can keep things in a kind of steady state on the ground here in a way that it's harder in space. And so you have to be really cognizant, and the people that drive these telescopes, the Space Science Telescope Institute, they have to calculate precisely where you can look in the sky and how the angle of the telescope can be relative to the sun. So that's one of the big constraints. And so if you request an observation of a certain part of the sky and you want to look at it in a certain orientation, there are very specific times of the year that you can do. And so that planning can be very difficult. I have observations that I've taken with Hubble, and it was really hard to do those observations. So they're just little tiny windows. And then if you miss it, you have to wait a year. Or if there's something wrong with the observations, like the gyroscopes were failing on the Hubble Space Telescope. And so it wasn't picking up stars in a way that would guide stars in a way that kept it in the orientation that you wanted for the entire observation, so you get streaking in the image. And so some of the observations that we took, we had to retake 5 times, and each one of those had to be done at a very specific time of year. So it took 3 years to get those observations correct. So that's one of the main constraints. Even the what they call the point spread function. So like take an infinitesimally small source and the spreading of the light, that changes pretty dramatically with the thermal properties of the telescope. So again, the kind of thermal breathing of the telescope can actually change the optics, which then can change your measurements. And so like one of the things that a lot of people do with these space telescope observations, because they have really precise like morphological details that can pick up things like very precise shapes of galaxies, is gravitational lensing. Have you guys all heard of gravitational lensing? It's basically you have a mass somewhere in the universe, and it acts as a magnifying glass. So it literally bends the light around it. So you can pick up sources that are fainter than you would be able to otherwise. So you basically have cosmic magnifying glasses. And so the thermal expansion of the optics can actually distort the shapes in a way that looks very similar to lensing, and can actually completely mess up your measurement so that you get a poor measurement of the mass of the thing that's doing the lensing, or the distribution of shapes of galaxies, which can actually change your conception of the universe. So it's very important to take those factors into account. That makes sense?
I have a question, Brian.
Yep, please.
So earlier we were looking at the instrument mount, and we saw Igrans 2 and the wonderful CASI team. You talked about how it takes a crane to move the instruments around because you change those out. Now, is that you and the science team that go up to the summit and change the instruments, or is that a different team?
Yeah, so as I said, we have Gemini has 2 telescopes, one in the north, one in the south, one in Cerro Pachon in Chile, one here in the north. So each site has about 80 staff, give or take. And there's whole groups of people that have different specialties. So I go up to the summit, to our summit facility, once every 2 months, roughly. And that's mostly so that the people that actually know what they're doing can show me what they're doing so that I can then understand better what we're doing at nighttime or what the science demands are for people. So I was just up on the summit with Cicero, actually, and another staff on Tuesday of this week, and we were watching some basically the tearing apart of GMOS and the refurbishment of that instrument. We were doing, I wasn't doing anything, but the people up there were doing precision measurements with lasers through the optical path of GMOS, and they were actually projecting that laser onto a wall and measuring the movement with like a measuring tape to millimeter precision. So they would shoot this laser through GMOS, project it on a wall that was about 5 meters away, and then they would watch the spot move up and down as various optical elements moved. So this is the day crew and instrument engineers. These are people that do I would say the 2 hardest jobs at the observatory are day crew work. They typically leave around 7 o'clock in the morning. They go up to Halipahaku. They have breakfast up there, and they wait about 15 minutes after breakfast, and then they drive up to the summit. And so I don't know if you guys knew this, but if the summit of Maunakea were about 70 feet higher, I think, OSHA would require that everybody wears oxygen. So it wouldn't be a debate. You would have to wear oxygen up there. It's not, and so oxygen is optional. How did you guys feel at the summit? Did it feel okay? You know?
It's pretty rough.
It's pretty rough. Yeah. Yeah. I mean, for me, it's like a 50-50 shot. When I go up there, like sometimes I'm feeling fine. And sometimes it's just like, it's tough. Like you can't think, and then because you can't think, you're like, oh, I could totally like run up those stairs. That's fine. And then like you end up horizontal and you don't know what happened. Okay.
It was fine.
Yeah. Yeah. I mean, it's usually like 1 out of 3 people that get hit pretty hard with altitude sickness. And so we have oxygen up there. And so like we always check like pulse ox, check the oxygen saturation. If people look dizzy or whatever, then they go immediately on oxygen. On any given day, probably day crews, probably 6 to 8 people. There's going to be people with oxygen, even to people that go up every single day. And so they're up there from 8:39 in the morning all the way to 3 or 4 in the afternoon. And not only are they there, they're not just sitting there, but they're moving around 3-ton instruments on top of everything else. So it's like heavy manual labor that they have to do on the summit with, fairly large drive time, acclimation time, everything. So that is one of the hardest jobs here. I would say the other hard job is the night crew. You have to stay up from, come in, you have to prepare starting about 5 p.m., depending on the time of year. And you're staying, depending on how mean your Q coordinator is, you're staying probably until about anywhere between 5 and 7 in the morning. So some of the calibrations that we take actually occur after sunrise. These are like the worst night. So when you see that in the plan, as an observer, your heart drops or you just run away as fast as possible, and save that for another night. So yeah, it's a tough job at the summit, for sure. It used to be that we observed from the summit. Cicero does observe from the summit. I've observed from the summit before. You basically have to know your plan before, ahead of time, because like doing high level thinking at the summit is not something that most humans are capable of doing. So oxygen deprivation sucks.
We have about 1 minute left in this special session with the brilliant Akamai interns. And Brian, oh, I see Cicero is in there with Jenny and with Adam doing active troubleshooting, I assume, since she is one of the support science migrants too.
Yeah, this is the other part of the job is it looks easy until things break, and then it's just a night of troubleshooting. So this is a new instrument and it's got some little issues, and there's a new issue that's been popping up, and yeah, I haven't seen it before, and yeah, we're trying to figure out what's up with it.
Yeah, so this is one of the downsides of complexity. So when you're running 3 to 4 instruments at nighttime, each one of those individually can fail. Luckily, we have backups, we have backup plans, other instruments, but it's just more moving parts, more components. Any other last questions, guys?
Would you say like generally sometimes like is it the instrumentation issues occur because of like a code issue or like a engineering issue, I guess,
Or an operational issue?
or an operational issue?
Human error. It's all of them. Like honestly, the distribution is all over the place. Software is tough, and like as Jenny mentioned, like sometimes we have software built in house, sometimes we have it built elsewhere. So like some of this software that's for the Zygrins 2 instrument that was developed by the CASI team, by the Korean Space Agency, and we have to like interface it with our systems, and that interfacing process can be incomplete, and you know basically everything's going to be stress tested. We're always going to like go to edge cases, always going to be, because we have this huge temporal baseline we observe every single night, and so something is going to go wrong, and then we learn from it. And if things don't come back here, we'll probably abandon this instrument and then throw it to the software engineers tomorrow. So this is probably a software issue right now, if I read the error message correctly. But we have all sorts of like, we as scientific like operations support staff, we have to take like what observing team, what they want, and we have to translate that into our language and our observing scheme. And that can be a very complicated process, and we can screw that up for sure. And then we pass that to the nighttime observers, and they say, "What the hell are they doing?" And then they have to either try to push through and fix it, or they kick it back to us and they say, "Hey, that was stupid. Try to fix it, whatever." In nice language. Adam's always very nice, very polite.
Well, Brian, I think we've come to the end of this special session.
Yay, we made it, guys.
Yes. You know, one of the things that I really love about hosting Shadow the Scientist is that it is observing in real time. Nothing is, it's not curated. This is what's really happening. So you got to see lots of action in the control room. You got to not only talk and hear from Jenny and Adam, but you actively see how Cicero, as the support scientist for Zygrins 2, because she's right here, they're using her expertise, pulling her into the control room to troubleshoot this issue. And this
Making
is
her blush.
Oh, sorry. But this is, you know, I want to highlight this because this kind of collaboration and teamwork is what makes any organization work well, but especially when you're doing this kind of precision work. This teamwork and communication is absolutely essential, and I'm glad y'all got to see that. I'll leave it with Jenny. Adam, do you want to wrap us up here?
Hold on.
Oh my.
The file. Let's see.
In what way? Just to say my goodbyes and thanks for involving us in your Shadow the Scientist special event.
That'll do it. Yes,
Sounds so nice.
absolutely.
Yeah, I don't know what else to say. Thanks for joining us, and we're still trying to collect some migrants to data, hoping it's actually working. Yeah, exactly. Cross fingers. Only one finger. If you only cross one finger, it's good luck. Cross two, it's bad luck. You just negated it.
Oh no. Well, now you tell me. I didn't
Anyway,
know.
yeah, so long night ahead of us still, and thanks, guys.
Thank you, Jenny. Thank you, Jenny. Thank you, Cicero. Thank you, Adam. I don't want to disturb Cicero and Adam there. Brian, you have been amazing bringing the Akamai together, you and Cicero. Thank you so much for the opportunity to connect you all. And for all of you brilliant interns, I hope you have a fantastic rest of your time at your respective facilities, and wishing you great success in all of your projects.
Thank you, Jamika.